Hello, welcome to Richardson RFPD's Tech Chat. I'm Kirk Barton, Field Application Engineer for Richardson RFPD, and I'm here today talking to Eric Benedict, Senior Application Engineer for Analog Devices, and we're going to discuss common mode transient immunity testing as it relates to gate driver products. Um, so, Eric, can you talk about the test fixture used for testing CMTI and maybe go through an explanation of some of the waveforms that you measure in order to get to the results?
Sure, happy to. So, here at Analog Devices, we're very interested in making sure we're providing parts that have, world-class common mode transient immunity. And so we've been developing different generations of test fixtures to let us do that. So here's our latest iteration of a test fixture that we're using for testing our and our competitor parts. So we have a very controlled, repeatable system that we have where, we basically put the part under test on a little test card that then plugs into the fixture. So it's very repeatable and controlled. Our fixture, we're able to apply a transient, with rise times anywhere from about 3 nanoseconds to over 13. And then we have a power supply, that we can adjust the magnitude of that step from about 0 to about 1.3 kilovolts. We can do positive and negative steps, and we can control exactly when we apply that transient relative to the signal being sent through the gate drive type of thing. So we can adjust that, and we can basically see in a controlled manner what happens to the gate drive when you have a transient that happens at different times. So as part of our studying for that, we tested over 20 different parts, both from us and our leading competitors. Basically would apply a transient at different times, multiple times for each time step, and then basically sweep through the logic transition and see what happens with the part. So for example, here's a part where we have an input waveform and an output waveform, and then an applied common mode transient. The scope shots here are infinite persistence, so it's basically the same thing time after time after time. The input is unchanging because that's fixed, but then you can see the timing variation that happens when we're applying a transient at different time locations. So here, the center plots, we basically with the timer, we're able to record the deviation in the timing based on when we applied the particular common mode transient. So basically here, the time scale for the phase is relative to the input edge. So that's right here. And then you can basically see that, we're stepping through from minus 40 nanoseconds to 20 nanoseconds after the transition. So to 80 nanoseconds here. And basically you can see as you start to apply transients at different times, there's a different impact in what the timing transient is. So here, this is 150 kilovolt per microsecond part. We're applying 120 kilovolt per microsecond transients in each of these. And you can basically see we're introducing up to potentially 30 nanoseconds in timing jitter. Okay. Which is, half of the propagation delay you can see for that. In comparison, here's one of Analog Devices, similarly rated 150 kilovolt per microsecond part. Again, we're applying 120 kilovolt per microsecond transient, and the propagation delay is, worst case, 5 nanoseconds peak to peak variation. So, considerably tighter in the performance, much more immune for what you're looking at.
Right. Okay. Now, so if you getting right down to it, if you look at ADI gate drivers, how do they compare to their competition?
Okay. Well, I think they compare pretty favorably. So here is a survey that we did with 100 kilovolt per microsecond rated parts. So we have analog devices parts along with 1, 2, 3, 4, 5 other competitive parts. Now there's a range of ratings for parts, and so I was trying to pick parts that when I looked at the data sheet, they were saying, or claiming 100 kilovolt per microsecond performance, because it's not much of a comparison if you pick a 20 kilovolt per microsecond part, compare
Right.
that to something higher. So
Right.
tried to make it fair, and so went through, selected a range of parts from different manufacturers and tested them. And so now one of the things to note, we got a log scale here, and I am taking the common mode stress well past the 100 kilovolt because I want to see how well the part works. So with with a couple exceptions, all the parts performed okay in the region of 100 kilovolts per microsecond. When I went back to look to see what happened with these parts, it turns out they talked on the front page of the data sheet 100 kilovolts per microsecond, performance and things like that. But when I go back and look at the data sheet, it was closer to 25, 30 kilovolts per microsecond was what they guaranteed. So you got to look at the data sheet a little bit closely. But even then, you can see there's a range. Here, no stress, they're all pretty tight, but then in their timing jitter. But as you start to apply CMTI, it starts to grow. If we run them at the maximum that our fixture can do, these are all 100 kilovolt per microsecond parts, so that they're on a spec. Okay, that's not surprising, but analog devices parts, we're still at spec, even at 3 times the CMTI.
Oh, wow. That's good.
Okay, so with our parts, there is plenty of margin. You don't have to worry about it. And this carries through even to the higher rated parts, 150 and 200 kilovolt per microsecond parts. Here, the parts are better performing, so we're not having to exceed the jitter. I don't have to go into log scale for that. But even still, again, the ADI parts are very low jitter, even at the high limits. And, our 150 kilovolt per microsecond parts are outperforming competitor 200 kilovolt per microsecond parts. So
Yeah, that's good. Yeah, that's much lower worst case jitter than the competition. That's great. That's a great summary there, Eric. Is there anything else you'd like to add?
I guess just look at the data sheets closely and realize that perhaps testing or looking things that just because the data sheet says something doesn't mean that they all perform equally. And as our testing is showing, our parts have superior common mode transient immunity.
Great, great. Well, thank you, Eric. We appreciate your time today, and thank you all for watching our Tech Chat video. You can learn more about this and other topics on the Richardson RFPD GAN and SICK Tech Hub. Follow our Ask an Expert link to submit questions relative to the design challenges you may be having.